There's two things. I want to talk about the relationship to compiling and programming languages. Some of you may really know already what this relationship is. I keep mentioning it. I use only like alphabets that are zeros and ones. Like we talk about 0 to the n, 1 to the n, and strings like that. And I keep saying, oh, this has a lot to do with programming languages. And you might very well feel, I don't know what it might have to do with programming languages. So you might be able to make the analogy yourself. But I'm going to make the analogy explicit. And this won't take very long. And I'll try to relate it to what you often see in programming language books, little syntax diagrams in the back that describe the syntax of the language and how it relates to context-free grammars and how it relates to something that is Backus-Naur form, or BNF. That's a way of describing programming languages as well. And that fancy-sounding term is just another way of writing a context-free grammar. What I hope that Rusty and Dimitri will be able to do, either next recitation or this recitation or both, is talk about the tools lex and yak that are built into Unix that really do these things practically. We're going to spend 10 minutes on this, but you can spend a whole course on the parsing part of this relationship to compiling and programming languages. All right, number 2 today. It's very, very useful to be able to take an arbitrary context-free grammar and change it into something which is more specific, that you can assume certain structure about. I told you that context-free grammars, have a single terminal on the left, single non-terminal on the left, but anything can be on the right. It'd be nice if without any loss of generality I could say, well, the right actually looks like this. Particular kind of things in the right without losing any generality. I mean, if you do something like this, the right side has to look like, small terminal, big non-terminal. That does restrict your grammars and takes you back down to the finite state machine level. So is there something in between where we can restrict the right side? Now, why would you want to do this? People always talk about these special kind of forms and don't really motivate them. So I'm going to write down the form that we'll talk about today, and then I'll motivate it before we do it, because it's really an important thing to do. So there's a lot of different normal forms or restrictions to the right side that doesn't really lose you any generality. That means that you could take any context-free grammar and convert it to something in a particular, more restricted form. One of them is Chomsky normal form, another is Greibach normal form, and there are others. Chomsky normal form is a very useful one for at least 4 different reasons that I'll list here. And that's really the interesting part of this lecture, is why it's useful and how it's useful in the next upcoming lectures. The actual details of converting something to Chomsky normal form, which I will do today, frankly, I think is like the driest part of the whole course. It's just relatively straightforward algorithms, but some subtleties, and you need to know how to do it. So we'll do it, and I'll do some examples. So here are the motivations. Number 1. Now I'll make it letter A. Motivations for Chomsky normal form. Every string of length n is derivable in 2n minus 1 steps. If you have just an arbitrary context-free grammar and you try to derive a string, that's going to end up with 5 symbols, how many steps does it take? Well, the answer is you have no idea. You could build that set of things way up high and then erase things with like e-productions until they're way down to 5 symbols. You could actually go 100 steps to end up with something that has 5 symbols. So there's no limit to how long you have to try in order to find out whether you can derive a string. You just have to keep trying things, and you don't even get any handle on an upper bound. But in Chomsky normal form, every string of length n is derivable. If you can derive it, you can do it in 2n minus 1 steps. So that's really useful to know, because then the question of whether we can write an algorithm to decide whether the grammar does really derive this string, and that's the same algorithm as parsing in the compiler, the question of whether that algorithm exists is immediately implied by this, that there exists an algorithm. The algorithm implied by this is really an ugly one. It's try every single production, to a depth of 2n minus 1. And if you don't get the string then you can stop. How long does that take? Let's say there are, average of 3 productions every time that you have a choice for, and you're going to do it to a level of 2n minus 1. How big is that tree? It's a tree of 3 raised to the 2n minus 1. Very bad. It's a horrible exponential time algorithm. We're going to do much better than this, but at least this immediately implies that there is an algorithm and that it's not undecidable. And that's useful. All right, B. That's actually the least useful of all 4. The next 3 are even more useful.
2n minus 1 is the upper limit, right?
Yes. In fact, it'll be exact.
It will be exact?
It'll be exact. You can do it. If you can do it, it'll take that many steps. No more, no less. Yeah, the very nice Chomsky normal form. The fact that grammars can be put in Chomsky normal form makes us have a very easy proof of the pumping lemma for context-free languages. We're going to do a pumping lemma for context-free languages. That's much more complicated than the pumping lemma for regular sets. The proof for it doesn't come from a machine. Remember the proof for finite state machines come from a machine because there was that loop? That was the whole idea in the proof. You don't get that loop that you can guarantee for push-down machines. And you'll see why when we talk about them. It doesn't work the same way. The analogy doesn't carry. So you know where you find the loop for context-free languages? You find the loop in the grammar derivation, in the parse tree. And where do you find the loop? You find a non-terminal in the parse tree repeating itself further down the path. And that's where it doubles and builds up. And you get a more complicated pumping lemma because of that. Just intuitive. If you don't get the details, don't expect to. It'll take a whole day to discuss this pumping lemma. But the description of it on that day will be much easier if I can tell you at the beginning, let's assume the grammar is in Chomsky normal form. Because it makes my argument much easier, and I don't have to deal with a bunch of very boring technical exceptions. It gets rid of all the exceptions for me. C. One of the big things in this level of theory of computation is that context-free grammars are going to be equivalent to non-deterministic push-down machines. Okay, they're the same thing. If you have a non-deterministic push-down machine, you can convert it to a grammar. And if you have a grammar that's context-free, you can convert it to a non-deterministic push-down machine. Those are the same. The equivalence of those two is nowhere near as obvious as any of the equivalences we did at the finite state machine level. But one direction is made very, very easy if you have Chomsky normal form for the grammar. And that direction is that if somebody gives you a grammar, you can construct a machine that accepts the same thing that the grammar generates. So I'll say every CFG has an, quote, equivalent non-deterministic pushdown machine. That's 1/2 of the equivalence. This direction, that given a grammar you can get a machine, is very easy to prove if we know the grammar's in Chomsky normal form, and a pain in the butt to prove if we don't. By the way, the other direction, that if you're given a machine, there exists a grammar, is so difficult that I usually don't do it in class the first time that I'm teaching people this course. I usually wait for the second course, because you can spend 2 days on it, and I'm not sure it's possible to really pick up the main point the first time you see it. But it's hard.
10 words on what a push-down machine is? Is that a machine that uses a stack or something?
Yeah, you want 10 words? Here it is.
That's 4 right there.
Okay, I got to be careful. Oh, I used them up. All right. A push-down machine is a finite state machine that every time it moves from one state to another can also push and pop arbitrary symbols on a stack. That's what it is. It says, give the finite state machine a stack it can manipulate. If you give the finite state machine 2 stacks, it's all the way up to Turing machine power. So it's a nice hierarchy. Give it 1 stack, it can do push-down machine. Give it 2 stacks, everything. OK, D. There is a good algorithm for membership in context for membership of strings in context-free grammars. Not a real practical one, but a lot better than this exponential one. It's one that we talked about in the algorithms class when we talked about dynamic programming. We talked about a parsing algorithm. It's called the CYK algorithm. That algorithm is very easy to describe if the grammar is in Chomsky normal form. Much harder to describe otherwise. So it's the CYK order n cubed algorithm for the membership problem. And as I mentioned in algorithms, and I'll do here also, I like to do this because at least it shows that the problem is polynomial time. But nobody would ever use this algorithm in practice for a real compiler because there are linear time algorithms for compilers that work with what are called LRK grammars, with a special subset of context-free grammars that can be parsed much, much more quickly, and that correspond to the deterministic context-free languages, to the subset of context-free languages. And those are the ones people really use, and all of those are unambiguous, and they're fast to parse. And we can get it down from n cubed to linear time. OK, so that's the motivation and where we're heading and why we're doing all this stuff. So we're going to go back here to number 1, then do number 2. And if we have time at the end of the day, I'll go ahead and start talking about pushdown machines and doing some examples with them. OK, who's got questions then?
I guess Chomsky did the same linguistics.
Yes. Maybe Todd can. When did Chomsky do this hierarchy? In the 50s?
55, 56.
55, 56.
Before he came to MIT to teach French, technical French.
Technical.
There wasn't a linguistics department when he came to MIT. But
I see. But he certainly did this from the point of view of linguistics and not from the point of view of computer language theory.
But his background was both mathematics and linguistics.
All right, I'm going to put a grammar up on the board that looks really different than the grammars we've been putting up so far. The grammars we've been putting up so far have zeros and ones and just a few non-terminals. The grammar I'm putting up on the board now is meant to be a fragment of a grammar that really generates a legitimate programming language, like something you'd see in C or something like that. So here it is. It's going to take up most of this half of the board, and it's not so complicated, but it'll make the connection from context-free languages back to practicality. So here it is. Anything that I enclose in angle brackets is meant to be a non-terminal. Okay, so normally I would just write capital A here, but I want to make this a semantic so you understand it. So this means a statement. A statement can be, in a language, can be a bunch of things. It can be an assignment statement. It can be an if-then statement. It can be an if-then-else statement.
Are you writing something that's just a context-free grammar, or is Chomsky normal form?
This is nothing to do with Chomsky normal form. Right. This is just number 1. I'm just trying to make the connection to compiling and programming languages. So let's call this the start symbol of our grammar. A statement in our language can be one of these 4 things. It can be an assignment statement, an if-then statement, an if-then-else statement, or it can be a begin-end block. Okay, that's like the open braces and closed braces in a lot of languages. All right, so now these are all non-terminals. So just this or this or this or this. We have to say what each of these are. You see things like this all the time. You see this in XML. You see it in any kind of language that you have to describe what the structure of the language is. And it's just a context-free grammar. But I want you to realize that we're not just talking about weird equals, zeros, and ones all the time. It's really the stuff you see in every textbook. I was in Barnes & Noble's last night. God knows, there's 800 books on every, learn, what was it? A whole book on 800 pages on how to use the new version of Quicken. That's like, and then there's 80 books just on XML. Anyway. Here's the if-then statement. The if-then statement actually has some terminals in it. Anything that isn't in angle brackets is a terminal symbol. Think of this as like a 0. It's a token that stands alone. Okay, IF is like a single terminal. So if, the word if appears, then comes something we'll call an expression, which is angle bracketed because that needs to be expanded later on. If expression, then terminal symbol, then what? Then statement. right? This is too easy? Just not too easy. Okay, worth looking at. All right. I think this is really important, but maybe some of you just know it. And if you do, fine. If you don't, let's go through it. I think this is worth seeing, making the connection. As I said, this is a thread we could travel down for a whole semester, you know, and talk about LRK grammars and compilers and write a compiler and forget about the Turing machines. But we're not. Just 10 minutes today. All right. If expression, then statement, else statement. Okay? So that's if, then, else. It's not hard. It's just interesting. Begin, end. Begin, end. Starts with the word begin, has a statement list in the middle, ends with the word end. This is actually just like a language called Pascal. C uses open curly brackets and closed curly brackets for begins and ends. They call them blocks, whatever. Java does the same thing. But in Pascal, they use the word begin and end. Not the biggest difference between the languages, but at least one minor difference. What's a statement list? This is for the first time you have to think about, remember you did some exercises with Dimitri yesterday about how to make context-free grammars for certain kinds of languages? So right now, in the next step, you're going to have to remind yourself of that kind of exercise. What's a statement list going to be? Just describe it to me in English first, and then we'll write it out. A list of statements, one after the other. At least one, and possibly many. How do we write that? Yeah, it has to be at least one. All right, so you know what? I'm not going to do this in a context-free grammar right now for the following reason, because I want you to realize that sometimes people don't write context-free grammars like context-free grammars. Sometimes they make pictures, and they call them syntax diagrams. And they're just the same thing, hidden in a different form. Syntax diagrams and Backus-Naur form and extended Backus-Naur form are just convenient ways of writing context-free grammars down. So here's a syntax diagram for this that I think is very intuitive. You can have a statement, you can be done, or you can go back and have another. And when you're done with that, go back and have another. Everybody understand what that syntax diagram means? It means lots of statements, at least one. All right, so let's turn it into a grammar, and in doing so, teach ourselves how to take any syntax diagram, which is nothing more or less than just these loops with things on them, recursively rip them apart, and turn them into grammars. So let's do the simplest version. How do we take this little loop and turn it into a grammar? I'll do it right underneath. Statement, list, followed by statement. What's the idea there? If you repeatedly now substitute statement list again, it becomes statement list statement. Statement list anchors on the left and builds up as many statements after it as you want. This is just like 0 star. Nothing more or less than 0 star. It's just lots and lots of these. And how do you terminate? With a single statement. And if you want it to have no statements possible, you terminate with an empty string. But we want to have at least one statement. By the way, in Pascal, you can have no statements in there. So this isn't exactly Pascal. OK, so this diagram is the same as that grammar. What haven't we expanded yet? What's missing? What non-terminals are just sitting there? We need assignment, expression. So let's start with assignment. Assignment has some identifier, which we'll call ID. That's like some variable name. Colon equals. That's directly from Pascal. That's Pascal's way of distinguishing assignment from equality testing, the same way C uses double equals compared to assignment. Expression. Please don't ask the following question. In C, these expressions are actually identical. Any expression can go any place, and every expression has a meaning and returns a value. Pascal was actually a fussier language, and this had to be a Boolean expression, and this had to be, well, it's a little, the grammar in reality might be a little different, but I don't want to make it too complicated. But you might want to separate and make a different non-terminal for this kind of expression and a different one for that. And you might not. We're not. Yeah, Teresa?
What does it mean to be a terminal? Like, what is that?
The terminal means that it's going to sit there when we're all done and be something that gets generated from this. It could be part of the language when we're all finished. These angle bracket things will all disappear, and when they do, there's going to be nothing left but if A equals 3, then
There'll be nothing left but terminals? Or there'll be
nothing left but terminals. The terminal symbols are the things that are left over when you finish generating the string.
Okay, in fact, that something starts out like if isn't different than the letter A. I mean, it seems like you're using terminal at a higher level in combination with these non-terminals, but you're not using A in combination. Does that mean there's any difference between IF and A? I mean, they're both ultimately terminals, but...
No, there's no difference. I mean, A is a very... In fact, no, they're the same thing. IF and A or 0 or anything else would all be the same. Same terminals, no difference.
This is just like HTML, all its little tags disappear.
Now you're confusing me. Not exactly. This represents a structure that lets you, build things. I think you understand that this lets you build these long strings that end up looking like Pascal programs. So when you're finished building one of those programs through this structure, all the angle bracket things have disappeared. But it's not because somebody processed them and they're tagged open and closed. It is the same to the extent that some program looks at this thing, looks at the tags, takes the tags away, and then results in something in the end.
Yeah.
But what happens in the middle is really quite different.
Sean?
Yeah.
Is there a reason you're specifically tying this example to Pascal rather than some other language? Is it more suited to this? Or?
Pascal's simpler. The whole syntax diagram for Pascal takes 2.5 pages. I could Xerox it for you and hand it out in the back of one of my old Pascal books. And that's why we do it. And in fact, if you look at any problems, there's a problem a little bit similar like this in your own text. They're always done with these kind of old languages because the new languages are just too ugly to give a real picture of. Especially, Java's got, I don't know how ugly it would look, but it would be a lot more complicated than this.
Try.
Yeah.
If you were to have like symbols, like let's say you needed parentheses around the if-then expression, would they show up here
Yes.
as a terminal?
Yes, they would. In fact, where they really would show up would be in the expression itself might allow parentheses, and then they would show up as terminals in the productions of the expression. But yes, parentheses would show up as terminal symbols in these things.
But they'd show up in the expression, not in the if-then.
Probably. Well, no, if we insisted on the expression being surrounded by parentheses, no matter what, regardless of the expression, then it would show up right here, open, close. But the expression itself might have parentheses, which get generated by its own productions. Okay, so yes to both parts, really. All right, where are we up to? What else haven't I done? Expression I haven't done, right? And I haven't done ID. I'm not going to do expression because it's complicated. It'll take a long time. But you know what it's like? Remember what I did the other day? S goes to A plus A, B times B, and then those symbols. That's very close to what an expression is. That for production grammar that generates expressions. I am going to do ID, though, because this will give us another practice with converting syntax diagrams to context-free grammars. What's your typical identifier in a programming language? Typically, you have to start with some letter A to Z, and then continue with letters A to Z, followed by digits 0 through 9, and maybe some other symbols as well. And you can go as long as you want. Here's what it looks like. A letter followed by a letter or a digit. Let's just say that's all you can do. And then you can end. That's a syntax diagram. Start with a letter, continue with any letters or digits.
So you're requiring it to be at least 2 letters or 1 letter and a digit?
At least 1 letter. It doesn't have to be 2 letters.
It doesn't have to go into that loop?
It can, no. can go right out. And of course, we can add underscores or dashes or anything else you want to allow in identifiers in this list. All right, how do we make a grammar to do this? And you don't do it in one production this time, or in two productions like we did before. In fact, you can't even easily just do it using a single non-terminal. So let's think about how. Basically, here's the idea. Anytime you see a loop in a syntax diagram, pull that out and identify that with its own non-terminal. So what's really happening here is that an ID is a letter followed by, I'll call this temp, followed by this loop. Anytime you get a loop, yank it out and make it its own procedure, so to speak. Okay, take it out of the recursion. So ID, letter, temp. And temp has the recursion on it. What is temp going to look like? It can be temp followed by a letter. That's this loop. It can be temp followed by a digit. That's this loop. And what can it terminate with? Well, temp starts here, so it can terminate with nothing. Okay? It doesn't have to terminate with a letter or a digit. It can actually be no occurrences. So this gives you, this is just like 0 plus 1 star. I can have any letters and digits I want in any order I want, and then I can stop, including the empty string. So that's what you do. If you see a syntax diagram, look for the loops, yank them out, identify them with their own non-terminals, and then put the placekeeper back in here. So ID goes to letter temp, and temp has this loop in it. That's enough of an example for if I made you do it, and I probably won't, for you to go look at syntax diagrams and unravel them and turn them into grammars. But enough for you to get the sense that they're the same. Backus-Naur form, BNF, is very much like these grammar situations. An extended BNF is like these syntax diagrams. The syntax diagrams is a pictorial version of extended BNF, which basically lets you say letter followed by either letter or temp repeated as many times as you want. It looks like the kind of stuff you get in Tickle when you have regular expression generators. Looks a little like that. Yeah, Kevin and then Joe.
You're not allowed to assign a value to a word like begin or if, but this production could generate those words. So how do you prevent that from happening? Does it just get really complicated production-wise, or is there like a more simple way to short-circuit that?
That's a really good question. That's an excellent question. It's an excellent question. I'm hesitating because I don't really have the time to give you a really good answer for it. Here's the short answer. The short answer is that there's a whole bunch of words in the language that are reserved words that cannot be used as an identifier. And those are enumerated and taken care of in this parsing step so that you would never accidentally generate them here. I mean, all right. It's a lot to talk about there. Yeah, John.
If you had a limit on the variable length, like they could be no longer than 15 characters, how do you figure that into there?
Not that way. Anybody have an idea?
15.
Right, you have 15 non-terminals. You just remember. You use your non-terminals to remember a count. The thing about context-free grammars is that they can represent infinite things, but if you want them to essentially be finite, you're just going to have a lot more non-terminals to remember how far you've gone. So you'll have one non-terminal that says, this is a 15-letter string. That depends on a 14-letter. That depends on a 13-letter. What's a one-letter string? Single letters. So you can do that. Letters and digits I didn't write out either, but it's kind of obvious. Letters go to terminal symbols, A, B, C, D, up to Z. Digits go 0 through 9.
We can't
And there's a fragment of a grammar here. Yeah.
We can't leverage the power of our stack that we've been given by being in a no longer just a finite state machine to keep track of how many we've got.
Sure you can. You don't need to, though. I mean, if it's finite, then even a finite state machine can do it.
Right, but if
You just don't need that power for what Joe asked.
We're doing 200 allowed a variable length of 200. You don't want to have 200 different states, do you? 200 different.
No, you don't really. So when you implement it, right.
The other thing, actually, the way C works is you can have variables as long as you want, but they only recognize the first so many characters. So they just let you make up strings as long as you want.
Right. So the grammar will parse it and say, okay. You see, you're asking questions now that are bordering on the other course of compiling. There's three parts to a compiler. There's the scanner. That's the part that uses a finite state machine. That's the part that the tool lect lets you do quickly. The scanner looks through the language and pulls out things like IF and spits it to you in a chunk instead of you having to look at it at the character level. So it pulls out the tokens. It lifts it up one level of abstraction. And pulling out and looking for tokens, you can do with a finite state machine. The next step is you're given tokens, something that looks like a potential string in your language, and you want a program to run through this grammar and check if it's syntactically correct. And that's parsing. And that's what we're really talking about. And then the next step, which is a good third to a half of the compiler course, is now that you've done that, how do you generate the code and make the thing run? And that deals with symbol tables and all sorts of issues that come up with different ways of solving the kind of things that you're asking. And that we're not touching at all. Not that it's not interesting and it's not practical, it is. It's just a lot. And we don't have anywhere near the time to squeeze it into this course. It's always a separate course.
Is parsing also done with a context-free grammar?
Yeah, parsing, yes.
Parsing and scanning.
Scanning is done with a finite state machine.
Oh, with finite
Parsing is done with a context-free grammar. And the tool for parsing is a tool called YAC, yet another compiler, where you basically describe your context-free grammar, and it automatically builds a program that will do the membership test for you. And depending on who you talk to, like lect, it automatically does the finite state recognition for you when you describe your finite state machine. A good programmer and a hacker says, I'll make my own finite state machine recognizer. I can do that. And before you know it, he's already coding. And while you finish your conversation, it's already there, and it's 50 lines long, and it works perfectly fine. And I'm not going to go learn how to use lect, because it's a pain in the butt. I have to learn this new syntax when I can just write it on my own from scratch. It's a good point. You can write it on your own from scratch, and there's no reason not to. It turns out that the lect is a really good tool, and that almost anything that you do from scratch on your own is going to be less efficient than the one that lect does automatically for you, and be slower. And what's more, there are things that, once you do get used to lect, are just much more convenient and really do speed you up. So it's like any tool. If you use it a lot and you get used to it, you should use it. And if you can use it once in a blue moon, it's not worth learning. Anyhow, it's a cool tool. And Rusty, when are you going to do that? Tomorrow, maybe?
Either this afternoon or tomorrow.
This afternoon or tomorrow, Rusty will show you a good example. What did you do? You made a scanner that looks for...
I think we're just going to do a calculator.
A calculator, okay. So the parsing part is checking if it's the correct expression, and the scanning part is pulling out the digits, the numbers. Okay. Everybody get the example that we'll do? It's a perfect example. Perfect. I don't get it. Oh, I get it. Okay, we're up to Chomsky normal form. Here's all the great motivations. They're all so interesting. They're all so neat. You'll appreciate them every time we get to these stages. And now we're doing it. And like I said, I got to tell you, it's dry. I don't like it, but I need to teach it to you. And I will try to make it as interesting as possible by inviting people up to dance in between each step or something. I don't know what we'll do.
We get a star system.
Where's our professional dancer isn't here today, so what are we going to do?
Jeffrey will dance.
Jeff will do the discrete math dance? CNF, Chomsky normal form. CNF also stands for conjunctive normal form, which has nothing to do with Chomsky normal form. That's a way of taking logical expressions and making them with ands and ors. And that's also written CNF. I don't know. It's not like a domain name service, where you have to pay for your abbreviation and then nobody else can use it. But people write them both. Chomsky normal form. Here's what it is. Every single production looks like this. Capital letter, double capital letter on the right, or capital letter, single terminal on the right. That's it. Every production, double capital letter or single terminal. Double non-terminal or single terminal. And That is enough flexibility to capture any context-free language. You give me a context-free grammar, I can convert that context-free grammar to one that looks like this. And in many ways, it's the best you can do, because you know that if I insist on this capital B being a terminal symbol, we're at the regular set level. If I insist on this capital C being a terminal symbol, we're at the regular set level. So this is a pretty simple grammar to be able to capture all the possible grammars available. All right, all productions look like one of these. How do we show that any grammar can be turned into a grammar like that? Step by step by step, we will do it and try to make it intuitive. I want to motivate this a bit. So all right, there's a fraction of a grammar at least, completely not in Chomsky normal form. I want you to think about what kind of things do you have to do to get this into Chomsky normal form. Not the details of what you have to do, but the big picture. What kind of productions do you have to take care of that are bad, that mess you up? Well, there's one that's okay. That guy. So if you got any of these, leave them. That's easy. These are bad. They're too short. These are not allowed. Only real terminal symbols, not ones that don't have any content, like the empty string. Empty string productions are not allowed. Only real terminal symbols. That's what lets us have that 2n-1 thing, because you never erase symbols. You grow them and you grow them until they hit the string. You don't erase them. So empty strings don't exist in these. So that's bad.
But recursion on S is okay. S goes to empty. You said
No, I'll get to that.
okay.
Clever question. Yeah, I mean, Todd, look, what if the empty string's in the language, right? I can't just leave it out completely. So there's one exception to the empty string. If the empty string's in the language, you make a new start symbol that goes to S and the empty string. That's the only exception to Chomsky normal form, is that if the empty string's in the language, you're allowed one single, non-terminal here and one empty string there. Otherwise, it really is consistent. 2 non-terminals, 1 terminal. I don't know if that's what you meant, but it's kind of what you meant. You will not ever get S going to empty. If it happens, it's going to be filtered at and look just like this. This is the only time you'll see an empty or what's called a unit production. Only 1 unit production allowed. This one's no good. Too short. Too short. This one's no good. Too big. Yeah, Chris, what are you thinking? Nothing? All right. These are really short. Definitely no good. These don't even seem close. Which of these problems seems hard to you? Which seems easy? Tell me how to solve any of these problems. Can you solve any of them? Can you fix any of these productions? Sure. Without losing the acceptability of this, without losing the semantics of the grammar? Sure.
You said you could.
You trust me? After all these months, huh? All right, somebody there said sure. Who said sure in the corner? Joe. That's because he trusts me. Yeah, Joe, you got an idea?
Well, I would start with the A0, 0A, 1B.
All right, how do you get that to do anything? I mean, that's got terminals in the middle, for crying out loud, right? That's just a mess.
I would convert that to, say, 1 terminal and then 2. Can you add letters? Yeah.
You can do anything you want, as long as it doesn't
And
change
then
the...
add 2 letters, so that which would represent those 4, that repetition. So, kind of say, let's see, A can go to 0, which would be the terminal to show. I'm assuming the A is 0A would be A would be a repetition. So it would be A can go to either to 0 or to, let's say, GG, which would represent and then GG can go back to itself or 0.
I'm not following, because GG, you can't have GG on the left side of something.
Okay.
And
But what I would add a new letter.
It's definitely a good idea to add a new letter.
Okay.
But before we add them, we still have these zeros and ones in there that we have to get rid of. So we're going to do that adding. That's a good idea. But what about these zeros and ones in the middle?
So anything
Let's
that's
break it into
terminal
two. Call it S goes to G and H and symbols.
And then
All right, right, that's good. But I want to first get rid of these terminal symbols before I do that. I mean, because this early step that I'm suggesting is much easier than what you guys are suggesting, which is the right answer. But before we do it, why don't we just say Z goes to 0, O goes to 1, and O stands for 1, O-N-E, right? And then every place you see a 0 and a 1, you're putting capital O's and capital Z's. So now you don't have any of these issues of having terminals in the middle. Now everything just looks like capital letters. Now we can do your trick, right? So ZAOB. Now this looks kind of just like this. Now, in fact, Zaub, twice the caffeine, half the intelligence. Zaub. And it'll sell too, that's the thing. Now all the examples can be divided into very simple categories. Either you have productions that are too long, or you have productions that are too short, or you have productions that are... All right. Let's do the long ones first because they're easy, or at least easier. And both Doug and Joe have the right idea there. What we're going to do for long ones is we will kind of group them. We don't have to group them 2 and 2 because that's specific if we happen to get 4. But we want to make it more general grouping. But basically, what we're going to do is think of this as two things. Z followed by AOB. And the AOB will be represented by some new letter that we've never seen before, say M. And M goes to AOB, and M takes the place here.
Why not have a non-terminal point to 2 of the first 2 symbols?
To do it 2 and 2?
To 2 at a time, since that's our limit.
No reason. This is just systematic. Maybe we could do it that way. If there is a reason, I don't see the subtlety why we can't right now. So we repeat the process. Now OB gets blocked up. We'll call that N. M gets to be OB. And we're done. This is S goes to ZM. M goes to AN. N goes to OB. And make sure that these M and N appear nowhere else. There can't be any connection with them in the rest of the grammar. They are simply placeholders to make this turn into things of 2. And you're thinking, well, we're not really doing anything. And that's true. We're not. We're just moving things around so that we can always assume that we can do this and we can have 2 non-terminal symbols in every production. And if the other steps were just as easy, it would really be easy. But the other steps are a little bit harder. So these we're going to leave. These long ones we'll take care of. The terminals that are in the middle we can take care of. The things that are hard that are left over are the E productions and the unit productions. Because those you can't just group together and pull away. And they do have semantic meaning, and we have to capture all their semantic meaning.
So now we have M as AN, but S is still has to be Z-O-Z-M.
ZM.
I got it.
And it has all the, we haven't lost any meaning. Okay so far? All right, so now I'm going to concentrate on how we take care of E productions and unit productions. And here there are some subtleties, and I will start with hiding the subtleties completely. And you know what? Our book completely hides the subtleties. In fact, he doesn't mention them at all. If you actually tried to implement the algorithm he suggests and wrote the program, there would probably be a bug in your program that you wouldn't find until somebody typed in a particularly nasty, sneaky, context-free grammar, and your program would bomb because he doesn't mention it. But you know, he's right not to mention it because it's just ugly and it takes away from the main idea. But I'll mention it after you get the main idea because I want you to see it. All right, where are we? Here we go. Let's say we have a production like this. Z, N, O, N, Z. and another production like this, n goes to the empty string. Let's say these were the only productions in the grammar. We'll isolate a little magnifying glass on this picture. We would like to get rid of n goes to the empty string. We would like to cross this out. But we don't want to lose any information that this production gives us. So what do we need to do not to lose any information and still be able to cross this out? What we're going to do is we're going to imagine that we went to every other production in the whole grammar where n appears, and we make n disappear. We do the substitution in advance and leave all the possibilities intact in advance. What does that mean? In this case, there's two different n's. So here's what we add on. The first one can disappear. So A could go to Z-O-N-Z. Zons.
But in this case, n can only disappear. There's not enough.
I know, I'm right. Right.
Wouldn't they have to, all of them disappear? So wouldn't A have to go to Zaz? Okay.
All right. I mean, it's a fragment of the whole grammar. I'm just focusing on the one part. So imagine that other things are there. Don't think this is the whole picture. What else can happen? The second one could have gotten.
This is something you do when non-terminating symbol repeats itself. Or this is something you do when.
This is something you do with every single E production. You take the E productions. We're getting rid of E productions now. I'll summarize all the steps at the end in an orderly way. But we talked about how to get rid of long productions. Now we're talking how to get rid of E productions. Here. Actually, long productions is what you do last. Long productions. E productions you do first. And unit productions you do second. We did this first because it was the easiest one to explain. Now we're doing E productions. You take every single E production. In this case, there's only one that we see. You go to every other production in the whole grammar, namely just this one, because it's the only one I have on the board, and you substitute for n in every possible combination. N goes to empty. So you get zons, you get znaz, and you get zaz. And you need all three of those. If there were 3 n's in a production, how many would you add? No, 2 to the third, because it's 0, 1. But the empty string you never add in, so that takes care of 1. And the original you don't add in because it's already there, so you end up adding 6. Here we added. You are clever. All right. Everybody get that? That's more or less it. You go through all the different E productions. For each one, you go through the whole grammar, make your substitutions, and then get rid of the E production. Goodbye. Same thing if S had an E production. You do the same thing for that. If S goes to E, go through all the things, substitute, then cross out S goes to E and make this thing so that you don't lose the fact that S can generate the empty string. So if S goes to E, you have to do that. All right. So that's the basic part of this stage. But I think it's a good time to look at the subtlety here, because otherwise you'll forget what's going on. Not you personally, but one might. Here's a made-up grammar just to point out the subtlety. It's not an interesting grammar, and it's only a fragment of a bigger grammar, but it will point out the subtlety. Let's go through our algorithm, pretending we're the machine on this, and see what happens. Who wants to start?
We're doing unit production.
We're doing E production still.
Okay.
We're still here. We just want to see if there's some subtleties. Right. Who wants to start?
So we just
Go ahead, Chris.
we just have to assume that x can go to e, so along with going to XO, we can go to just to O.
Good. So the only E production we see is X goes to E. We look through all the other productions in the whole place, and here's the first. So we add on
X.
O, right? Because X can go to E. Does anybody see why we do E productions before unit productions? Because you get unit productions when you do E productions. So that order is important. What's more, well, all right. What's less?
Y can go to X. So anything that Y can.
Right. You start seeing this problem here. What's going on? The next thing you might like to do, X goes to E. Do you make this substitution? No, because it's just going to add Y goes to empty. You don't ever want to add E productions in these substitutions. So it looks like we're done, I guess. But it's not true. We're not done. We missed it.
Z, Y, Z.
Because X can go to Y, Y can go to X, X goes to E, so Y can also go to E. But we didn't even know that. So what the first thing you have to do is not just look for E productions, but look for what are called, it's got a fancy name, nullable non-terminals. In other words, non-terminals that sooner or later can disappear, not necessarily in one step. Everybody get that?
Is there a limit to how many steps they...
No, it might take 100 steps. You got to keep checking. How do you check for nullable non-terminals? This is like a simple loop. Start with all the E productions. What are they? X goes to E. Now, look for all productions that contain just X's or E's, or combinations of them. Well, not that one. That's got an O in it. Not that one. That one. So you just work your way backwards from the base case, looking for right sides that have just empty strings, finding all the non-terminals that can go to them, and then you get a new set. So first we started with empty string, then we get X and empty string. And now we look for all productions that can go to things that have combinations of X's and empty strings. That adds Y. And then you do it again. What if there was a production that went to XY? Say S goes to XY, then we would add S to that list. What happens is you keep doing this, and suddenly in one stage, you get the same thing you had the last time. And then you stop. And you have to be able to stop because this could only get so big, it can't keep growing. You only have so many non-terminals. This is a completely decidable algorithm. It's easy to do. Simple loop. It's very recursive. You could also write a tail recursive. There's a lot of easy ways to do it. But you have to find the nullable non-terminals. And when you do, you write them all down. X and Y. And then you do the substitution simultaneously. You go through everything and you add them all in. So not only do we add O here, but we also add ZZ. And then we can erase all the E productions. Who had a question back here? Joe.
There's no reason why every symbol couldn't go to something for the E string, right?
In this case, they don't.
In this case, they don't, but I'm saying there's no reason why Y, or let's say Z couldn't go to 0 in the E string. And let's say that was your whole grammar. Is that true or not true?
That Z could go to 0 in the E string? Sure, it's possible.
Okay. So like if of all your terminals go, one of the elements that it can go to is the E string, what do you do?
I mean, if everything's nullable,
Right.
you just run through, make all the substitutions, and then cross out all the epsilon productions when you're done.
You would just, okay.
Just do it the same way. You don't do anything special. It would still work. You wouldn't get any weird thing. The only thing you'd have to do at the end is add this, because S could generate the empty string.
And then you get all of the permutations of things that S can go to.
Yes, you'd have tons of extra productions by doing it, but that's what you get. You have to do that to capture all the meaning of the grammar. Right, sure. Yeah, Sharon.
We don't have to do anything with that X goes to Y, given that Y is in...
No, because we're actually going to get rid of it in the next step anyway, these unit productions. But we wouldn't get rid of it because it has meaning part of the meaning is that it captures the E production, but if you erased it, you would lose other things. Because what if Y went to other stuff? You really don't want to just get rid of that X goes to Y yet. You want to get rid of it and make sure you don't lose information, and we would lose information if we just crossed it out.
But you dropped the E.
We dropped the E, right. This is now gone. Absolutely. Yes. Okay. Questions?
Yeah.
Yeah, Seth?
So once we make this substitution,
Yeah.
you added the S line. Do we cross out that X goes to Y or the E production?
We cross out the E productions, but not any of the others.
Okay, all right.
Not any of the others. Just cross out the E productions.
But it does seem like we're losing information by keeping that Y there, because if Y were with something else, we would or a possibility that the Y just went away, like we do with ZYZ. Now we have an or of ZZ.
Mm-hmm.
But I mean, I guess there's no way to account for it with just one symbol, but it does seem like we lose the possibility that the Y just goes away. That the X points to a Y and the Y goes away.
But we haven't lost that possibility because the Y can just go away and the X can go away because the Y can go away. And anytime the X and Y can go away, we've handled all those situations.
Okay.
So we haven't lost any of them. Every place we saw an X, we got rid of it, and every place we saw a Y, we got rid of it, and those can continue on from there.
Okay.
So we haven't lost them. It's a good thing to think about, but we haven't really lost them. All right, so that's E productions. Questions about that?
Grammars have to terminate, right?
You mean they have to be finite number of non-terminals? What do you mean they have to terminate?
Like that wouldn't be complete because Z doesn't go anywhere, and you'd never be able to terminate Z.
I see. You're bringing up a point that I'm going to do at the very end, which is you can have grammars that have what are called useless symbols. We don't say they terminate or they don't terminate. We say their symbols are useless. We're much harsher. And it is important to get rid of all the useless symbols because they don't do anything. And the normal place you do it is, well, you can do it in lots of places. You could do it in between every step, and certainly you should do it at the end. But often you do it at the beginning because it cleans things up for speed, and then you do it at the very end. It is possible to generate useless symbols depending on what happens as you go along. So you want to do it once, and I'll show you how to do that. And that's completely reasonable. All right, questions? All right, let's do the number 2, and that'll finish the whole picture. Unit productions. Say you got A goes to B, and you got B goes to, I don't know, bozo, CC, ABC, and I don't know, that's it. Oh, I don't know, and 0 and 0. Well, here's what we do. If you have a unit production, you want to get rid of it. Now, let me add a few things here just for here. So say A goes to a bunch of things, including a single B. And we want to get rid of this. Bye-bye. How do we get rid of that without losing any of the information that that production normally let us have? Yeah.
You convert B into all doubles and then put the doubles into the B.
What do you mean convert B into doubles?
So that they're all 2 characters long like they're supposed to be.
You mean make this BB bozo?
No.
What do you mean?
Like you break the bozo
Fix the
up.
long productions.
Do the long production on all the B's, on bozo and ABC.
Yeah.
And then take that whole string and substitute it in for B.
Okay. But why do we have to do the long ones? Why can't we just substitute them straight before doing the long ones? Do we have to do the long ones first?
No, just thought it'd be easier that way, but you can do it the other way.
Well, because we do the longs at the end, but we.
Otherwise, you've copied them. This way, you're copying them all and then have to.
Oh, I see. Yeah, so maybe we could. But the second thing you said is the key, which is whether you do the long ones now or later, what you really have to do to keep this semantic interpretation intact is A goes to B, B goes to all these things, so A goes to all of these things. It's as simple as that. So we're going to add on to this list boso, CC, ABC, and 0. Okay, and now you can cross out B. Everybody see that?
We don't need CC twice.
What would duplicate?
Yeah, I guess we don't need CC twice. That's right. But it don't hurt. Right, you don't need it twice.
Is there a minimum Chomsky normal form?
I don't know. I think not. I don't think so. Good question.
These are really sets, not lists, right? So we should.
Right.
Even sets.
Right, right. It's, you really can't have CC twice there. Okay. Nobody's wondering about it, so I won't mention it. That's that's all right. Where was I here? All right, we did E-production, we did unit productions, we did long productions. All right, now some subtleties with unit productions. Here's another example. S goes to A, 1, 1. A goes to B, single 1. B goes to S, single 0. Ow. All right, you're a computer, and you were told to look for unit productions and then go ahead and copy all the other productions you found there, not creating any new unit productions, ideally. So let's start with S goes to A. What do? We go down to A, and we see that A generates B in 1. So we don't add B here. That we don't want to do. We don't want to add new unit productions. But we are going to add in 1. Now we can cross that out. A goes to B. So we go down to B. That means this goes to 0. By B. And now B goes to S. And S has 1, 1, and 1. So we put those both in. And now we're done.
Why did we not put the S on the A line?
Because that would give us a new unit production that we don't want. We don't want to make new unit productions while we do this. But the implication of your question is, good. I mean, this isn't right. We missed something. Because S can actually get 0. We didn't get it. How come? So, look, this doesn't happen so often. It happens when you get these chains that recursively go back in unit productions. You could go, a year and your program would never see a grammar like this. And the first day it sees a grammar like this, it's going to give you the wrong Chomsky normal form. So what's the subtlety here? The subtlety is what you have to do is similar to what we did with nullable productions. When you look at a unit production, you don't just look at that unit production, but you go forward and look to see if the A has any unit productions. And you make a list of all the single non-terminals that S can get to, even if it's by more than one step. So before we went backwards from the E to the front, now we're going forwards from 1 step to 2 step to 3 step unit productions. So what are the unit productions for A? What are the list of them? It goes, for S. It can go to A and it can also go to B. What about for A? A goes to B and B goes to S, so it gets 2. And what about B, S, and then A? You first make these lists. So you have a whole list of the unit productions. And then you simultaneously, just like we did before, add all the productions in. So let's do the example again the right way. S has 2 unit productions, 1 away and 1 2 away. But together they're AB. Therefore, we look at AB combined and add all the things that AB go to. So we get 1 and 0. Then you go to A. Add all the things that B and S go to. What's going to happen is that every one of these will have all these things in them. And this way you don't miss anything. So it's the same subtlety as before, that it's possible that you have to look ahead to other extended unit productions the same way we had to look ahead to extended E productions. Okay, questions about this? When we started this grammar, it looked like this. What does this grammar generate? Generates 3 strings, right? 1, 1, 1, and 0. If I take away any of these productions, one production in this grammar, does it still generate those 3 strings? So anything you can get rid of and have it still generate those 3 strings.
Well, you could remove the 1, 1 if you're allowing repetition. I mean, you create a 1, 1 by 2 A's.
No, but there's no way to get 2 A's in here, right? So we couldn't do that. Is there anything useless here? Anything that isn't getting used? We need the A, it goes to B to be able to get the 0. I don't know if we need B goes to S. Might be able to get rid of that. I don't know. But we certainly can't do much to this grammar. Look at this grammar, the resulting grammar. We don't need any of these. All these 6 productions are completely useless. You can't get to them at all once the unit productions are gone. Okay? I showed you before how E productions can give you unit productions, and now I'm showing you how when you get rid of unit productions, you can actually get useless symbols. Symbols that do nothing for your grammar. The whole grammar is S goes to 1, 1, 1, 0, and I got this A and B now that I've erased the unit productions of, and who cares what they can do because I can't even get there from S. So the last part of the day, I want to talk about getting rid of useless symbols. And I want you to do it at the beginning and at the very end because the procedure can actually generate more useless symbols. It's not enough just to do it once at the beginning. So Mike Sipser in his book doesn't talk about useless.
The order, though, is to get rid of useless symbols and then E production and D production belong.
And then, again, useless symbols, yeah. Where's my useless symbol? Okay, here we go. Useless symbols. Like everything in grammars, there's a subtlety here too. The idea is straightforward, and then there's a subtlety. And I'll put down the idea without the subtlety first. 2 steps to this process. Think of this as an example for your motivation. Why are these symbols useless? Because they can't be reached from S. If there was any production out here like A, B, then these symbols would not be useless. These symbols are useless because you can't get to them from the start point. Okay? It's like a big cave, and there's no way to get to a particular room from the opening of the cave, so what do you care about that room for? All right. On the other hand, there's another way symbols can be useless. Now I can get to CC, but I can't do a darn thing with CC once I get there because it doesn't exist in any other productions. Or even worse, it does exist, but it doesn't terminate. So there's 2 reasons you can be useless. One is because nobody can reach you, and the other is because once they get to you, you don't do anything useful. Okay, 2 ends on this. And we got to check both. And it makes a big difference which end you check first. So I'm going to write down the 2 things we're going to look for and talk about how we'll do it. So step 1 is find all the non-terminals that can actually generate something. This excludes things like C. Find all the things that actually generate something, that don't sit around and loop on their heads. Do that first. All the ones that don't generate anything, like C, get rid of them and get rid of every production in which they appear. So if there was a production here, BC, then after this step, we would get rid of this, we get rid of this, and we get rid of this, even though that B is in there. Okay, that B just got contaminated because he was hitched up with a useless symbol. So there's no point in keeping that BC anymore because C could never disappear, so who cares what B does in that production? Questions about this? We haven't talked about how we'll do this, but we talked about what it means. Now there's the second part. Find all non-terminals that can be reached from S. First, find the non-terminals that are useful, that can actually do something once you get there, that can terminate, and then find out all the non-terminals that you can get to from S.
Wait, so you're saying look for these things, but then you're saying remove the rest of the
Remove the ones that don't generate something.
Okay.
In this case, remove the C and anything that has a C in it.
Looking for ones that don't do anything useful and then eliminating them.
The way you've written it up,
I understand.
looks like we're looking for useful symbols, but we're finding all the things that are useful.
Because, you know, the way you really do it is you find the ones that are useful, because it's not...
And wipe everything else out.
Right,
Okay.
right. This is how you really do it. So I should say find all non-terminals that can generate something and delete the others from the grammar. Oh, I don't know. Write your own notes here. I hate this stuff. I'll tell you what I mean, and you can write it. Find all the non-terminals that can generate something, and keep those. That looks good. And keep those.
What do you do with the rest of them?
All the non-terminals, all the rest of them you get rid of, and any production that they sit in you get rid of. Okay, so it's not just getting rid of it and all its productions, but also any production that it sits in. Like that BC over there would go away. Here we find all the non-terminals that can be reached from S, and we keep them. And keep them. They're good. We like them. And all the others, we get rid of them, and we get rid of all the productions that they sit in. I think
Normal form has a start position.
the normal form has a...
Starting position. Start state.
Sure, it has a start state. Yeah, I mean,
Does it make sense?
every grammar has a start state,
What you
right?
just said? How could there be expressions that contain them yet they're not reachable? Unless the expressions are in other non-reachable states.
I'm not ignoring you. Let's do this example. I'm going to show you right now. You asked exactly the right question. Let's do this example. It's a very simple example, looking for useless symbols in this grammar. Let's do it in the correct order. Let's find all non-terminals that can generate something and keep those. Can A generate something? Yes. Can S generate something? Yes. So we keep them both. Does B generate anything? No. So we get rid of B, all its productions, and anything that B appears in. So step one gets rid of this. Everyone agree? Now let's do the last step. Find all non-terminals that can be reached by S and keep them. S can't reach any non-terminals. So we only keep S, and we get rid of A because A can't be reached. So this grammar ends up being just S goes to 0, which is right. All the other symbols are useless. I'm going to rewrite it over here. Let's do it the other way, just to show this very hard to predict subtlety. What if we did this in the opposite order, which is actually the way that a lot of people usually think of how to do this? Why don't we check which ones we can get to, and then check whether they can actually finish up? starting at the beginning, ending at the end. Why go at the end first? Why do it in this seemingly cockeyed backwards order? Let's do it in the opposite order and see what happens in this very simple example. In other words, first find all the terminals, non-terminals that can be reached from S. S gets to something with an A. S gets to something with a B. So everything can be reached. So as far as going forward is concerned, we think everything's hunky-dory after step 2. We can get to A and B. And now we go and do step 1. Which non-terminals can actually finish up and generate something? A can, S can, B can't. That's just like the first step we did last time. So we get rid of AB, because B is in there. And we're done. But we're not got the right answer. A goes to 0 is completely useless. We think it's useful because we did this stuff in the wrong order. And the reason for this is subtle. It's possible that you can actually get to something going forward that later on doesn't do anything useful, like B. And that was connected to A, which is the only way we knew we could get to A. And A did do something useful, but by then it's too late because we got rid of B and we no longer know that we can't get to A forward anymore. We got to check the forward last. It's a simple enough example so that if you look at it more carefully, you'll appreciate the subtlety. But it needs to go in this order.
And then we just remove the definition, or whatever you call it, of any non-terminals that can't be reached in the start state? Or what's it called, the whole row? You remove the whole...
All the productions with the non-terminal that's useless on the left side, delete them all.
But then the second step, you find any non-terminals that can't be reached in the start state.
Right?
And you delete their whole...
Delete any production that contains them either on the left or on the right.
Okay, so the deletion rule is the same.
Same exact rule. Yes, yes. Same rule, just different criterion.
So if it's on the left, you get more height.
Right. Yeah, Joe?
Could you do that again with B going to C and leaving C as the dead state? I'm just confused about how this works. All right, B went to C.
Okay. Let's do it again with this example. And that's it, and C doesn't terminate?
Right.
All right, so should we do it in the right order?
Yeah.
All right, let's find all the non-terminals that can generate something and keep those. While we're doing this, why don't we talk about how we're going to do that? How do you find the non-terminals that generate something? Start with the ones that generate something in one step, like A and S. This idea should look familiar. Those generate terminals in one step. How do you find the things that generate terminals in 2 steps? Find non-terminals that have combinations of A, S, and terminal symbols on their right side. Just look for things that have A's and S's and terminals. There aren't anything. If there were, then they could also generate terminal symbols. And then you'd add more symbols to that. And you'd do this just like we did with the nullable productions. It's the same kind of a loop. And you have to stop because you can only add so many non-terminals before you add a non-terminal. So in this case, the only 2 things that generate terminal symbols are S and A. Everything else we're going to get rid of. So B and C we're getting rid of. Bye-bye B, it goes to C. Bye-bye AB. Okay?
So that B in the AB goes in this step here.
Right. It's gone. It goes away in the step that we called number 1. And now we go ahead and do the second part. And let's talk about how we should do that. Going forward from S. Well, look at all the productions that S can get to and add them to your list. They can get to a production AB, so it can get to A and B. Oh, sorry, AB's already gone. So now there's nothing. But if it could get to AB, you'd list AB there. And then you go forward from A and B and see all the non-terminals that they could get to and list those. And go forward from those and see all the non-terminals they can get to and list those. Every single time you either add a non-terminal or you stayed the same. If you stay the same, you're finished. So how many steps can any of these loopy algorithms take? The number of steps equal to the number of non-terminals in the grammar. Because The slowest it's going to be is you add one non-terminal at a time. And then it has to stay the same once you get all the non-terminals. So looking forward in this step or looking backwards in the nullable, all of those algorithms take time proportional to the number of non-terminals. It's very fast. You could write a program to convert things in Chomsky normal form very, very quickly. All right, so anyway, Joe, so going forward from S here, S can't get to anything because there's no non-terminals in this list. Therefore, can't get to A, so we cross out A, and the only thing left is S goes to 0 again. Questions about this? I want to mention one more thing. We're done with Chomsky normal form, and I want to mention one more thing before we quit then. I won't start push-down machines today. I'll start them next lecture. Dimitri's going to do some examples of this stuff and of more grammar stuff. Then we'll do the Lex and Yak thing. Then we're ready to move on to machines. But before I quit today, remember I told you there's like only one interesting thing you can decide about context-free languages, and that's the membership question. And we'll talk about that in a separate day, a separate algorithm. But there's one other question that you can answer. Anybody remember what that is? Another question about context-free grammars? Almost every question is undecidable. The one question you can answer is, does a given context-free grammar actually generate nothing? That you can answer, yes or no. How do you answer that question now that we've done Chomsky normal form?
Does it only generate nothing, or does it generate nothing?
Nothing meaning the empty set, not the empty string. Generates nothing, not one terminal symbol.
It would all disappear in the Chomsky normal form if you just kept.
If you actually did the Chomsky normal form, you would have no grammar left. But you don't even have to do it that much. All you have to concentrate on is this last useless symbol part. All you have to do is check whether the start symbol is useless. And we have a two-stage algorithm that's completely loopy and loopy in a good way, and simple to do that. You can check whether any non-terminal is a useless symbol. If the start symbol is a useless symbol, it means the start symbol cannot generate any terminal strings. If that's the case, the grammar is empty. Okay, generates an empty language. That you can do. Asking the complement of that question, does the grammar generate everything? That's undecidable. That's much harder.
The complexity, the time complexity to get something into Chomsky normal form? Like how long does it take?
Where the size of your input, say, is the number of non-terminals or the number of productions, or so most of the steps are proportional to the number of non-terminals in your grammar, which is kind of constant relative. I mean, because the productions might be much longer than the. So the number in Chomsky normal form, the number of productions and the number of non-terminals is just related by a constant, right? Because you only have 2 in each one. So there's only one step that takes more than the obvious linear time. You tell me, what step can take a lot of time? That e-production step. If you have a lot of occurrences, you get that exponential thing.
Because of the subtlety?
No, because like if M appears 6 times in a production and it can disappear, then there's 2 to the 6 different ways it can disappear. That's the only time where you actually do something that tends to explode a little bit. But practically speaking, it's easy to do. It's not a difficult algorithm, and it's not an NP-complete problem.
Okay, that's right. You were just talking when you were saying to decide whether or not it produces the NP.
Right, right.
You said you put it in Chomsky normal form and then check to see if the start state is useless, or just
you can just take it from the beginning and say, is this start thing useful or useless by running this algorithm? You don't have to do anything as far as the other steps go. You just take the useless symbol algorithm and use it separately, and that's good enough.
Are computer languages put in this form?
No, I don't think so. My motivations aren't up on the board, but actually if you look at all those motivations, none of them help with compiling. They help with that order n cubed algorithm, which nobody uses. They help with a proof of the pumping lemma, which is an abstraction, but we don't actually have to keep anything in that form. And it helps with a proof that machines are the same as grammars. So it's mostly a mathematical convenience and not a practical convenience. Practically you come up with these things in an LRK grammar called LR items. And you make a big finite state machine out of them, and then you come up with a parser based on that. So actually you don't do this to do compiling. Other questions? Yeah.
Does Chomsky normal form allow the ORs, the bars between the different options? lines, or do you have to break that up into
Oh,
separate?
yeah, I mean, they allow it.
It does.
Yeah, I mean, that's just a writing convenience more than a rule about how many are in each one.
Right,
So,
well, it would mean you would have to rename it. You'd have to do S goes to A, B, or C, D would have to be rewritten.
S goes to A, B, S goes to C, D.
Well, if you don't allow the ors, if you don't allow it to have multiple ones, then you could
No, it's just,
add extra symbols.
I want to make sure I understand what you're asking because it's not,
I mean, it's just a writing convention to do that, but if you allow multiple productions out of the same S, that's
analyzed in the paper where there's only one production that has non-terminals, those are very special grammars. Maybe, I should just, here, I'll just, before we quit, we'll quit in just 1 minute, but last thing today before we quit. We talked about these special grammars, these single tree grammars that every non-terminal like S would have only one production. It might have a lot of terminals, but only one production with non-terminals. Special kind of grammar. And we showed that you can get equal zeros and ones. And I think Neil asked me, is there any set that you can't get with these kind of grammars? So here's a simple set that you can't get. You can't get 0 star plus 1 star with these kind of grammars. It's a regular set, you can't even get it. So if you try to make a picture, here's finite state machines, here's context-free languages, and you wanted to get a picture of the single tree languages, they're something like this. There are some finite state machines that are not in there. There are some context-free languages that are in there. They kind of overlap. So yeah, I think you asked that question yesterday. Somebody did. I'm not really sure. But anyway, even simple languages like this you can't get because you really need that union. You need two possibilities. There's a proof for it. That's the intercalation lemma. It's like a pumping lemma. You can really prove this can't happen. Anyway, that's way off topic right now. Let's quit for the day.